Okay, so this time we try to derive the same ODE here with the potential method rather than the power method. Okay, so here we also have this LRC or RLC circuit. So here we try to, let's say, define, this is VC, this is VR, and this is VL. Okay, so plus minus connecting back and forth, so that we can have VL plus VR plus VC equals 0. Okay, so I don't want to play with this plus or minus sign to which may if we have let's say if we define VL like this, okay, so we will have VL plus VC minus VL equals 0, then you may have more chance to make mistakes. Because usually if we just make it like this, if you make it like this, then for this inductor it is not VL equals LdIdt anymore. It is VL equals negative LdIdt. Okay, it lets you have more chance to make mistakes, so I try to avoid it. So I make this view back to back, and of course I will define I to be clockwise. Okay, so that it just follow all the V. Okay, making all the VI characteristic to be positive. Okay, so first of all we have a KVL, which is VL plus VR plus VC equals 0. Okay, so this is just as what I mentioned. Okay, so here for this VL is actually LD didt. Okay, LdIdt. VL equals LdIdt. And then for the resistor, it is nothing but the Ohm's law. V equals IR. And actually I write it as R times I. Okay, I try to put this unknown function at the back, and then VC IE, or let me just define this VC to be V. Okay, because I'll try to make use of this V, but I don't try to make too much subscript. 不想要太多下标，我就把 VC 写成V. Okay. And actually, we also have I equals C dV dt. I equals C dV dt for the capacitor. So I just write it next to it, because we cannot be able to substitute V by something else. This is actually like the first derivative of V times C is the current. Okay, so here actually we try to substitute this thing, okay, into here and here. Okay, so in this case we have L times C d2V dt2. Okay, first derivative, second derivative, and then C times L. So we have LC d2V dt2, and then plus R times C and then dV dt. R times C dV dt, and then plus V equals 0. Okay, so here we can just divide the whole thing by LC. Okay, so we have a leading coefficient to be 1. So d2V dt2 plus RC over LC. So it becomes R over L times dV dt. Okay, and then plus 1 over LC V equals 0. Okay, so this is what we need. What we need is this one, and so it has the same coefficient 1 R over L 1 over LC as this one. Okay, although this is Q, this is V. Okay, but just as what I mentioned last time, as this is a linear linear system. Okay, so this one you can just arbitrarily substitute any variable in this circuit. Okay, it will also satisfy. Okay, so yeah, so here we have a second order ODE, and we don't have anything on the right side because we don't have any source. Okay, we don't have any source, so it's just a homogeneous equation. Okay, so we can just make it like s square plus r over l times s plus 1 over lc times 1. Okay, I don't write it out. So this is the second order algebraic equation, or we can just call it the characteristic equation or the auxiliary equation of this homogeneous equation. Okay, so here, as this one, we have a 3 case delta to be larger than delta. Delta is b squared minus 4ac, which is r squared over l squared minus 4 over lc. Okay, so this thing can be let's say larger than 0, equal to 0, or smaller than 0. But actually we don't. We will just discard these these two larger than 0 or equal to 0. Yeah, because it will give you something like exponential to s1t and then exponential to s2t, and we have a positive coefficient, so which means that this s1 s2 will be negative. In such a way, we have something like exponential to negative exponent, which is something like this. Okay, decay, and then it will vanish. So we don't really like this because it's just like decaying. Okay, and for this one, it is something like a plus bt times exponential to st. Okay, similar things, we will have a positive repeated roots, so it is still like this. Okay, also tends to 0, yeah, when t is large, and no oscillation here. So this is what we want. And actually s is equal to 2a. 2a is 2, and then we have negative b, negative r over l, and then plus or minus square root of b squared minus 4ac is actually this one, r squared over l squared minus 4 over lc. And actually we can just put these 2 here and also inside the square root, so that it becomes negative r over 2l and then plus or minus. Actually we already know that this thing is smaller than 0, so that we try to write it as j, and then we have 1 over lc minus r squared over 4l squared. Okay, putting these 2 into this square root, it become 1/4. Okay, so this 1/4 cancel with this 4, become 1 over lc, and then r squared over 4l squared, and then we have a negative sign. Okay, because we know this is negative, so that we have something like -1 times this one. Okay, square root of -1. Okay, becomes this j here. Okay, so this is the root, and then this is the real part, this is the real part, this is the imaginary part. Okay, so the solution is strongly related to it. Okay, so let me try to cut it out. Okay, I put it on the next page. This. Okay, I just put it here. Okay, so we have these complex conjugate roots for the characteristic equation. So in such a way, we can actually write v of t equals something like v, okay, times exponential to negative rt over 2l, and then cosine this thing. Okay, this thing is square root of 1 over LC, and then minus R square over 4L square, and then times T, and then plus a phi. Okay, if we don't write it like with a phase, we can actually write it like A times this thing cosine of this omega prime t, and then plus B times this exponential, or times sine of this stuff. Okay, but for simplicity, we just make it like A times cosine plus B times sine to be a single cosine with a phase. Okay, with a phase. Okay, so actually here you write it as the omega prime t per omega prime t rather than that thing. Okay, so actually it's still defining that omega is actually 1 over square root of LC. Okay, so this thing inside becomes omega square, and then we also define that this is we don't define. Okay, we just keep it there, but we actually write it as V exponential to negative RT over 2L, and then cosine of omega, and then actually we define omega prime to be square root of omega square minus R over 2L, and then whole square, something like this. So it becomes omega prime t plus phi, something like this. Okay, so this thing is the real part of the root there. Okay, and this thing is the imaginary part of the root. Okay, so it is more or less like that. And actually we have a delta equals R square over L square minus 4 over LC to be smaller than 0. So it means that we have actually L is larger than 0, so we have a R square over L is smaller than 4 over C. Okay, or we can actually put it as something like R square is less than 4L over C, something like that. Okay, so which means that if we would like to have this RLC circuit to be oscillate, it should satisfy this condition. This R should be small. This R should be small, or R should be smaller than square root of 4L over C. 4L over C, something like this. Okay, so this R should be small enough, should be smaller than this value. If R is larger than this value, then this RLC circuit won't oscillate. And of course, this is for V, and then you can arbitrarily change it to I of t to be, this is also an I, this is Q, and this is also a capital Q. Okay, you can just change it to any variable in the circuit. Okay, any questions? Okay, so as an analogy, we try to, okay, I can just remove it. Okay, we can also compare it with a springless system. Okay, so here we try to have this spring K and then connect it to a mass M. Yeah, so last time if we compare it with the LC circuit, we don't consider any energy loss. Okay, so actually at that time we only have a force. Force due to this spring is F equals negative kx, which is the Hooke's law. But here we also consider it should have something like the fractional force. the frictional force or the energy loss due to the friction. Okay, 就是那个阻力啊，就是阻力。So this F is actually okay. So yeah, so this F is actually negative B times dx dt. Okay, or you can consider it negative BV. Okay, BV. Okay, so this is negative, which has the opposite direction as the velocity. Okay, and then multiplied by a coefficient, so it relates to how large the friction force is. OK， 就是那个阻力。那这个阻力这么 model 的话，就是比较合理的话，就是你往正的方向动，那你的阻力就是往负的方向；你往负的方向动，那你的阻力就是往正的方向。所以最简单的一个阻力的 model 方式是一次。有些地方复杂的，它可以加个3次，加个另外一个常数啊，就是减另外一个常数乘以 v 的3次方，但是就是 model 的问题。那简单的话就是这样。Okay, so in this case we have total force to be F. The total F is actually negative kx minus b dx dt. Okay, actually bv. Okay, but v is dx dt. Okay. The velocity is the derivative of the displacement. Okay, so we just write like this, and according to Newton's second law of motion, it is ma, so m d2x dt2. Okay, so in such a way we have m d2x dt2 plus b dx dt, and then plus kx equals 0, and then we divide whole thing by m. So we have a d2x dt2 plus b over m dx dt plus k over m x equals 0. Okay, so this is a similar second order ODE. So comparing with the RLC circuit, it will be d2v dt2 plus r over L dv dt, and then plus 1 over LC v, something like this. Okay, so we have a R over L and then 1 over LC. Here we have a B over M and then K over M. Okay, so you can just referring it like R to be B and then L to be M and then 1 over LC to be K over M. Sorry. K over M. This 1 over LC to be K over M, and then this R is referring to the B, and then L to refer to the M. L refer to the M, so C refer to 1 over K. Okay, so it means C is something like 1 over K. So just like here, we have all the equation for this RLC circuit. So if you like to have a similar version for this spring mass system, you can just do this kind of change of variable. Then you have the equation for this spring mass system. Okay. 所以简单来说的话，就是一个 spring mass system 跟一个 RLC 电路，它背后的数学其实是一样的是一样的。Okay, so here we have a sample problem. So it says a series RLC circuit has inductance L, capacitance C, and resistance R, and begins to oscillate at time t equals 0. At what time t will the amplitude of the charge oscillation in the circuit be? 50%. Okay, 50% of its initial value. Note that we do not know the initial value. Okay, we don't need to know the initial value. Yeah, because actually it asks you the charge. Okay, the amplitude of the charge. The amplitude of the charge. Yeah. So what does it mean by the amplitude of the charge? So when we have the expression qt equals capital Q times exponential to negative r over 2 lt, and then cosine of omega t plus phi. Okay, so actually the expression of Q is something like this. We consider this part is the amplitude. This part is the amplitude. Okay, this is the oscillation part. This is the cosine. So you can consider it is like you have actually a cosine. You have actually, or maybe starting from 1, a cosine, something like this. And then you also have an exponential. Okay, Q is the point at time t, and then you have exponential function like this. Okay, so this is a Q times exponential to negative RT over 2L, and then this is the cosine of something. Okay, so we try to multiply them together so that it turns out to be something like this. Okay, we have this is the so-called the envelope， 就是一个类似封包或者是一个包络。So this is the envelope, which is this is Q times exponential to negative RT over 2L, and then this is negative Q exponential to negative RT over 2L. Okay, so 它们是镜像 ，OK， 就是镜像的。那它乘起来之后，它就会是一个 ，so it will be like cosine, okay, but bounded by this envelope. Okay, it looks something like this. Okay, it looks something like this. Okay, so it asks you initial value is like this. It asks you when it goes to 50%. Okay, how long does it take? Okay, how long does it take? Okay, so actually it doesn't relate to this part. Okay, it only related to this amplitude part. So it is something like, okay, we have initial Q, and it asks you what is the T when the amplitude becomes half of Q. Okay, so the initial value capital Q is not important at all. Okay, we would only like exponential to the negative RT over 2L to be 1/2. Okay, this thing to be 1/2, so this whole amplitude to be half of capital Q. Okay, so we just take log on both sides, and then take or maybe we can just we can take the reciprocal first and then take the log. Okay, so we can eliminate the negative side, but actually it will be something like RT over 2L equals lateral log of 2. Okay, so if you take log first and then take the minus sign to the right side, so negative lateral log of 1/2 will become lateral log of 2. Okay, so we have RT over 2L become equals lateral log of 2, and we actually have a T equals 2L over R lateral log of 2. Then we can substitute the numbers. So we have a 2 times L is 12 times 10 to negative third power over R. R is 1.5 ohm, natural log of 2. So this is 11 millisecond, 11 毫秒。Okay, so for question B, how many oscillations are complete within this time? So which means that how many cycle of this cosine? Okay, within this 11 millisecond. Okay, so actually we need to calculate the frequency. The frequency omega prime is actually square root of omega square minus R over 2L whole square. Okay, which is actually square root of 1 over LC minus R over 2L whole square, and then we try to plug in the number square root of big thing, and then we have a 1 over 12 times 10 to negative third power, and then C is 1.6 times 10 to the negative 6 power. Okay, so this is 1 over LC, and then we have minus R is 1.5 over 2L, 2 times 12 times 10 to the negative third power, and then whole square, whole thing. Okay. Okay, so this is actually 7.217. Okay, so what is the SI unit? This is an angular frequency. Okay, this is an angular frequency. Actually, this is times 10 to the third, 10 times 10 to the third power. Okay, so SI unit should be radian per second. Yeah, radian per second. Okay, radian per second. Okay, so it asks you how many cycles are within this 11 milliseconds. So the number of oscillation is equal to 11 millisecond divided by the period. The period. This is the angular frequency. So what is the period? We should have omega prime t equals 1. Equals 1. Also, sorry, it should be omega prime t equals 2 pi. Equals 2 pi. Should be something like this. Okay, so it should be 11 milliseconds divided by the period t. Okay, so actually we have a t equals 2 pi over omega prime. Okay, so here we have a 11 millisecond times omega prime over 2 pi. Okay, something like this. And then we can put this number here. So 11 times 10 to the negative third power times 7.217 times 10 to the third power all over 2 pi. So this is 12.6. Okay, so we don't have any SI unit for it. It is just a number of oscillation. Okay, so which means that it actually takes 12.6, or you can say it is 12.6 cycles, which is something like, oh, this is 1 cycle, 2 cycle. Actually hard to draw. Okay, actually it takes 12.6 cycles. Okay, when the amplitude becomes half of the initial value. Okay. Okay. So next part we start to talk about something called a phasor. Phasor. Okay. Phasor. Okay. In this textbook, it does not mention about the phasor, and also I think the notation in this part in the textbook is quite strange, quite different from the formulas in the circuit theory textbook. So I already changed it from the textbook. Okay, so let's see it one by one. Okay, so we have 3 fundamental elements: the resistor, capacitor, and inductor. Okay, so we try to see it one by one. Okay, of course, the first one is the easiest case, the resistive load, the resistor. Okay, so here we try to connect a resistor with a series with a AC source. Okay, so this is an AC source, alternative current. Okay, this means alternating current. Okay, 交流电 AC source. Okay, so even though this is a voltage source. Okay, so you can see E here is an alternating EMF. Okay, alternating EMF. Okay, so we connect this one with a resistor. So actually for the resistor, it is too trivial. It is too trivial. So, but we try to follow it so that we have more chance to understand the capacitive case and the inductive case. So here we have the alternating EMF. E equals this. This is the amplitude. This is the amplitude EM, and then cosine omega d t. So this omega d is actually the frequency of this source. This frequency of this source. Usually, when we have the AC source from the socket in Macau, it is 60 hertz. 50 hertz. 50 hertz. 50 hertz. Yeah, in Taiwan it's 60 hertz. In mainland China, I don't really know. Yeah. So, but actually, we usually have this AC source to be 50 or 60 hertz. It has no relationship with the RLC circuit, with the oscillation frequency of the RLC circuit. Okay, so it's just the frequency of the source. Frequency of the source. Okay, the natural frequency of the RLC circuit can have a different oscillation frequency. Yeah, so here we have an E to be like this. So in this case, we only have this R. So the voltage or the potential difference across this resistor is nothing but this EM times cosine omega d times T. And actually we have Ohm's law. Okay, we have Ohm's law, which means that which means that IR is actually VR over R, so which is EM over R cosine omega dt. Okay, so looks very stupid. We only have this cosine here, and we have this EM, and actually we try to define this thing to be actually not necessarily the EM. And also we consider the phase. So we can consider this omega dt is like plus a zero. This is like plus a zero. Okay. So we try to define this VR is generally a complex number. 这个 VR 这个 phasor 一般来说是一个复数，但是在电阻里面它就是实数而已。它只是一个实数，它就是复数平面也是有一个实数轴嘛，所以它还是一个实数。那这个 VR 的话，就是说 VR 就会等于这个 EM 乘以这个 exponential J 零度0。那 exponential to 0 is actually 1, so it is nothing but VR equals EM. Okay, so EM. And similarly, this IR is the phasor IR is actually EM over R and then exponential to J0, okay, which is nothing but EM over R. So actually we have VR equals IR. Because if we have an IR times R, it is EM. So this is also EM is VR. So we have the VR equals IR times R. So you feel like it is quite stupid. It is nothing but the Ohm's law. Yeah, because V and I are in phase for the resistor. Okay, 它们同相位，所以这边就是好像跟普通的欧姆定律没有什么区别是这样。Okay, and here we will also define this is the impedance. This is the impedance. Impedance Chinese is called 阻抗. 阻抗 OK. 那 resistance 是电阻电阻。那是不是有电抗呢？是有的。不过我在这边就不讲那么多了。反正阻抗的意思是这个 Z general 是一个general 是一个复数，它是 R 加 JX。那这个是电阻，这个就是电抗。后面如果 RL 是有串联并联的话，它就会有一个序数的部分，那这边就会变成这个电抗的部分。 But anyway, for the resistor, it is nothing but R. ZR equals R. So it is also like a resistor. So the impedance of a resistor is still R itself. Okay. So on this page, you don't feel anything. Okay. It's just like very still things. But yeah. So for the second case, we have a capacitive load. Okay. So yeah, it start to have something interesting. Okay, so here we still connecting an AC source in series with a capacitor this time. Okay, with a capacitor this time. Okay, so this AC EMF, this alternating EMF is still E equals EM times cosine omega d t. Okay, and for VC is still the same thing. Okay, so here we have a actually VC still equals EM. VC still equals EM. Okay, so we write it as a VC equals capital VC. So this is the phasor of this VC. Okay, so this is actually a function of time. Okay, so this is a function of time. But this is a complex number. This is a complex number, and then cosine omega d, and then here we have IC. IC does not satisfy the Ohm's law anymore. Okay, because it's a capacitor. So here we have IC equals C dVc dt. Okay, so here we try to plug in this expression to here. We take the derivative, so we have C times VC, and then cosine, the derivative for cosine becomes negative sine, and then we have the chain rule, we have omega d coming out. Okay, so the expression will become this thing, but we still try to make it like we want to have a positive amplitude here, and then try to turn it into a cosine with a phase, okay, turn it into a cosine. So then this is the cosine, this is a cosine, and then this is the amplitude, and then we have a phase. This one is of course a zero, but here we have a phase. Yeah, because if we try to have a negative sign of something, okay, and then we try to make it positive, it should be cosine of this thing plus pi over 2. Okay, so this is like the identity in the trigonometry. So I hope you still remember. Yeah, so yeah, actually negative sign of omega d is cosine omega dt plus pi over 2. Okay, so because the second quadrant of the cosine is negative. Okay, so and then the second quadrant of the sine is positive. So here we have a negative sign. Okay, so yeah, so it becomes something like this. Okay, this is a positive amplitude, this is a phase. So actually the IC becomes omega d CVC, and then exponential to j pi over 2. Okay, we don't have 0 here because we have a phase, we have a non-zero phase, pi over 2. So here we have an exponential to j pi over 2. Okay, I hope you still remember what is exponential to j something. Okay, so exponential to j theta is actually cosine of theta plus j times sine of theta. Okay, this j is negative square root of -1. Okay, so if theta is pi over 2, so this is cosine pi over 2 is 0, sine pi over 2 is 1. So this is this thing is actually j. Okay, so we have a j omega d CVC. Okay, something like this. Okay, so here we still try to have something like ZC equals VC over IC. Okay, from this expression. Okay, which means that we try to move this IC to the right side and then we move this remaining stuff to the left side. So it becomes 1 over j omega dc. Omega dc, okay? So here we call this ZC is the impedance of the capacitor. Impedance of the capacitor. It becomes 1 over j omega dc. Or generally we just try to write it as a j omega c, okay? J omega c, okay? So we just replace this omega d by omega, okay, to simplify the expression. So this is the impedance of a capacitor. And actually this complex, this phase, okay, this phase is actually the phase between the current and the voltage for this circuit, for the capacitor, okay. And yeah, this J in the denominator means, yeah, this is a plus pi over 2. And next page, for the inductor, it will be minus pi over 2, okay. And then this J will go to the numerator, okay. So the things look like this. And actually, if we try to define CC equals VC over IC, you can also write it as VC equals IC times ZC, okay. So this is like generalized. We try to generalize the Ohm's law. The Ohm's law for the capacitor and also for the inductor in the next page. Yeah, but originally, if we write it as a time domain function of time, it turns out to be a differential equation. It turns out to be the differential equation. Okay, but yeah, here we try to introduce the complex number. Okay, play with the complex number is at least easier than solving the ODE. Okay, so the idea of phasor is like this. We try to creating something called phasor. Okay, so that we just doing the computation with complex number rather than taking derivative for the function of time. Okay, or solving constant coefficient ODE. Okay, so and then it turns out to be VC equals IC times CC, but it turns out VC, IC, CC are all complex number. Okay, and this complex number referring to the original function of time. Okay, so as they are complex number, it has amplitude and phase. So this amplitude and phase of the phasor is the same as the amplitude and the phase of the function of time. Okay, so yeah, so when we try to solve the circuit with AC source, with RLC, we try to change the circuit into phasor. Okay, the C turning it into something like this, and then also the source also turning it into a phasor. Okay, the phasor for this E is this EM. Okay, just ignore this cosine. And then we try to play with this complex number. Okay, so finally the solution is a complex number. And then we try to convert this complex number back to the function of time by picking its amplitude and phase. Okay, so the function of time will have the same frequency, and the amplitude will be the same as this phasor, the amplitude of the phasor, and the phase is also the same as the phase in the phasor. Okay, so for the next case we have, so yeah, it's the inductive load. Okay, so let me finish this page first and then we have a 10 minutes break. So here we have an inductor, so we have also the AC source connected with the inductor. So the same equation here. And then here we try to assume that IL equals IL times cosine omega dt. Okay, and actually for the inductor we have VL equals L di dt. So we try to put in this expression here. So we take the derivative, we have L times IL. And then the derivative for cosine is negative sine. So negative sine of omega d, and then the chain rule, we also have this omega d in the front. So we do the same thing, negative sign becomes cosine of omega dt plus pi over 2, like this. So actually, this is actually VL. Okay, we try to write it as the phasor form. So VL becomes capital VL, and then omega dL, and then this is also IL, and then cosine, and then we have an exponential to j pi over 2, and again this is j, so it be equals to j omega dL IL. And similarly, we try to have ZL is actually VL over IL. Okay, from this one, so we just move this IL to the left side. So the remaining thing is j omega dL. Okay, so which means we have this thing, or we can just ignore this thing. Okay, we can just replace omega d to be omega, so that it just consists with the previous page. Okay, CL equals j omega L. Okay, so this is also a complex number. Yeah, but this part is in the numerator, which means like something like a positive imaginary part. This is something like a negative imaginary part. If you just multiply j, negative j, okay, negative j squared becomes 1, and then so we have something like negative j over omega c. So it's like a negative imaginary part, but this is a positive imaginary part. Okay, so these are the phasor for the RLC. Okay, so R is easiest case, and then for the L is ZL equals j omega L, and then ZZ is 1 over j omega c. Okay, so